So we left off last time talking about different types of protocols. And do all y'all remember what a protocol is? You know, think of a protocol kind of like a language. And specifically the one where, yeah, specifically, the one we left off on is called IGMP, or Internet Group Message Protocol. And IGMP is one that allows multicasting to happen. And remember, multicasting is a point to multipoint. One node sends data to a group of people, and it's used for teleconferencing or video conferencing. One other place that I use multicasting a lot is in here when I clone the computers. And what I do by that, cloning means instead of, if we have new software I need to put on one of these computers, instead of installing it on every single computer, I install it on one, usually one of the ones up here in the front. And I make an image of that computer, and I send that image to my server back there. And then I put all these other computers in multicast mode where they're listening for the data to come out. And the data is sent from that server to each of the computers, but instead of having to send it 30 times, it sends it once, and every computer gets it that one time. The minus to the multicast is that it is there's no way for a computer to say that it didn't get a packet. So in my case where I do the labs like this, if one computer misses a packet, that computer fails out and the whole computer's down. But it's still so much faster because instead of sending 30 individual packets every time to every computer, I just have to send one. In here, it means cloning these computers takes about 10 minutes, and if I were to do it the other way, it would take about 5 hours. So it's a huge difference in time. ARP is another one. This is a network layer protocol. And what an ARP command does is it obtains the MAC address from the IP address. Now, do y'all all remember MAC address, physical address, all of those are the same name for the same thing. And the reason that this is an important protocol is that when you start sending data on a network, ultimately you have to have the MAC address to know where the data goes. Well, we use IP addresses at all the upper layers, so ARP is what allows us to figure out what the MAC address is of a computer from the IP address. And there's a little Windows command. Let me see if it works on Windows 8. If you type ARP-A, that shows you IP addresses and physical addresses that are known at the time for the computer. So see here, I have several internet addresses in my interface because I'm running VMware. But the one I'm actually using for, this lab, the 192.168.56.255, that's the broadcast for this. And ICMP is Internet Control Message Protocol. And what this does, it allows you to send out what's called a ping. How many of you have ever used the ping command before? All right, ping is a command that it's named that just from the old days of the military. What a ping does, you send a packet out, and if the server on the other end receives it, it sends back a yes, I'm alive. So ping allows you to see if a server is up, but it can't correct errors, it just detects them. Like, for example, one thing you can do if you're trying to see if your computer can get on the internet, you can ping google.com. And see, the first thing it does is it uses DNS to find out the IP address of google.com, which is 74.125.142.104. And then a ping in Windows sends out 4 packets, and you see that all 4 made it back, so there's 0 loss. So from that, I can tell that my computer A is connected to the internet, and B, Google's website is alive. Another one I use a lot is 8.8.8.8. That's Google's DNS server. So if you know that that is up, you know that your computer's able to get out on the internet, you're pinging Google's DNS server, and you're getting a response back. And the time shows you how long it took for that request to go there. Okay, so we've talked a little bit about IP addressing before. There's two types, IP4 and IP6. IP4 uses two address schemes, the logical and the physical. The logical is your actual IP address. The physical is your MAC address or your hardware address. IP4 uses a 32-bit number, and it's divided into what are called octets. In this example, 144.92.43.178, each of these is an octet. 144 is the first octet, 92 is the second one, 43 is the third, and 178 is the fourth. And the network class is determined from the first octet. And here are the different classes of addresses. You will need to know these for the Net Plus exam. A Class A address begins with 1 to 126 in the first octet. B, 128 to 191, and C, 192 to 223. Now, what number do you notice is missing from this?
127.
Do you know why 127 is missing? 127 is the loopback address. 127.0.0.1 is a very special address, and that's why it's missing from this table. You should always, on any computer, be able to ping 127.0.0.1. If that fails, then there is a problem with TCP/IP on that computer itself. So D and E are never used. Just be aware they do exist. D is for multicasting, and it's from 224 to 239. And E is 240 to 254, and that was for experimental use. So each of 8 bits, you have 256 combinations. 1 through 254 can be used as a network. 0 is a placeholder, and 255 is reserved for broadcast. So Class A devices share the same first octet as the network for the network ID. B uses the first 2, and C uses the first 3. So here we're showing that. A Class A address, the network information is in the first octet. A Class B, it's in the first 2, and a Class C, it's in the first 3. So here's our special address we were talking about, the loopback. 127.0.0.1. And that should always return, a valid ping if you ping it. In Windows XP and Vista and 8, all of the Windows stuff, the command ipconfig, if I could type, will give you the IP address of the computer you're on. So see there, I'm connected Wi-Fi. My IP6 address is up above it, but my IP4 address is 192.168.1.130. If you're on a Linux machine, the command is ifconfig. And I don't have a Linux VM up to show you, but it looks almost the same in what it returns. Make sure you know those two commands because you're probably going to see a test question on them. I had a test question that said something along the lines of ifconfig will give you the IP address on a Windows machine. And the answer was false. They were wanting to make sure I knew the difference, that ifconfig is the interface config command on Linux, and ipconfig is the one on Windows. This is probably the only Linux question you'll actually see on the Net Plus test, if you see it. All right, so the way that you write IP addresses, we use dotted notation, but you can write it in binary. And to write it in binary, you would convert each piece of the address over to binary, octet by octet. And the main reason you have to know to be able to do that is for subnetting. Now, luckily for y'all, there's not a lot of subnetting on this test. But I've gone over with y'all how to convert from binary to decimal, right? Make sure you know how to do that, because you may get a question on the test where they want to, they'll give you an IP address and they want you to convert it to binary.
Is that when we do that 1W2?
That's the table, yeah, exactly. All right, so the subnet mask is a 32-bit number that identifies the subnet. It's in 4 octets as well, and it's usually assigned automatically. The default subnet mask is always going to have a 255 in the network portion and a 0 in the host portion. So you see here for a class A, 255.0.0.0 is the default mask. For a class B, because the first 2 are network and the last 2 are host, it's 255.255.0.0. And for C, 192 to 223, it's the first 3 are 255 and then 0. Okay, so IP6 is something that's relatively new. And when I took the Net Plus, there was no IP6 on it. But IP6 is something that's becoming more and more prevalent. Eventually, the whole internet is going to move to IP6. And the reason is that we're going to run out of IP4 addresses. It is basically kind of the same thing the telephone company's trying to figure out what to do now. We're going to get to a point in the next 5 to 10 years where we run out of telephone numbers in the United States, because there's just so many that can be used, and so many are reserved for certain things. Like if you look at IP4 addresses, no number in 127 can be assigned. Nothing above whatever that class C is can be assigned. So there's lots of waste. It's kind of the same thing with the telephone system. We can't have an area code that starts with a 1 or a 9 because of 911, and then 1, is to show that you're dialing long distance. So IP6 come around, and instead of it being a smaller field, it's a 128-bit address. It uses 8 16-bit fields, and it's written in hexadecimal instead of decimal or binary. And here is an example of an IP address. And something that they want you to make sure you know, you can take the zeros out of an IP6 address, and they're assumed, and the colon separates each 4. You can also write zeros as nothing with just a colon. So that is the long form of that IP address, but in short form, that could be FE22 colon FF colon 2D colon 3012 colon CCE3. So you can take pieces of that out to make it easier to write. The reason that we've gone to IP6 is because we are going to run out of addresses, and there are so many more. I may have given you all this analogy last time. I get classes mixed up, but there are enough IP6 addresses that they could assign every atom on the Earth an IP address. And there would be enough left to assign 10 more Earth's addresses. This is a huge, expensive undertaking. Once we do this, we shouldn't have to do this again, especially in our lifetimes. IP6 is a multicast address used for transmitting to many different devices. An anycast is one interface group or group of interfaces. And all the modern operating systems can use 4 and 6. If your machine's got Vista or newer on it, it can do either. If it's XP, you can add IP6 to it, but it's not installed by default. So actual IP addresses are signed out by government-sponsored organizations. The IANA is one, the ICANN, and then RIR, which are regionals. They assign addresses to ISPs, and ISPs turn around and assign addresses to individual users. Every node must have a unique IP address. Everything on the entire internet has to have a unique IP address. Otherwise, it gets an error. That is why we're running out of addresses. There's a finite number in IP4, and so many people are on the internet now that we're going to run out. So there are static and dynamic IP addresses. And a static means it's manually assigned. You have to go into the network settings on that computer and put in the information for that address. A dynamic one is assigned by a server, and most places prefer dynamic addresses because then it's easier for them to change. In here, all of the computers are dynamic. The only things in this room that are statically addressed are the servers back there and then the switches. So DHCP is the protocol that allows a computer to automatically receive an IP address from a server. And I shouldn't really say server because most of you probably have DHCP at home too, even if you don't have a server, but your DHCP server is your wireless router or your cable modem. Reasons to implement this: it reduces time and planning for IPs, it reduces potential errors, it enables users to move workstations, and it makes IP addressing transparent for mobile users. Another reason to use it is that if you only have a certain number of IP addresses, but not all your computers are in use at one time, you don't have to give a computer an IP address if it's not in use. Look at this room, for example. I think most of these are actually on, so they've got an IP. But there's 4 of you in here. If we had a really limited number of addresses, we could just turn on the computers we need and they'd get the next available address. So even though there's 30 computers in here, we could get away with maybe only 10 IP addresses based on who's using what at what time. So the way DHCP works is with a leasing process. The device leases the IP address when it's on the network. The lease time is set by the server, and it specifies the address range and the lease duration. And if you do an IP config /all command, it'll give you information when you go down to the IP address about the lease. So see there it says that my DHCP server is 192.168.1.1. All right, so here's how DHCP actually works. The computer that needs an IP address sends out a broadcast that says, you know, what address can I get? The DHCP server then gives it an address. The client says, okay, I'll accept that address, and then the server blocks that address off based off the lease time not to give it to anyone else. So a lease is terminated based on a period of time that you set, or it can be manually terminated. On most DHCP servers, unless you mess with it, the default is 1 day. All of these, I think, are set to 1 day. So once you get an IP address, it's there for a day. All right, there's another set of addresses called private addresses. And these allow hosts to communicate across an internal network, but they can't be routed. IP4 has a complete set of addresses that are used for that. They're also sometimes called link local addresses. And there's a list of them we'll get to in a minute. But that's also what network address translation uses. Now, do y'all know what I'm talking about when I say NAT? What NAT is? Okay, NAT is what allows a computer to communicate without having an actual IP address on the public internet. Here at BIPSI, we only have a few public addresses. All of these computers are assigned private addresses. And the NAT, what NAT does is it translates that private address into a public address to go out and get data on the internet. And then the computer with the NAT server in it has a table that compares those addresses. And when the data comes back from the server on the internet, it translates it back into a private address to put on the network locally. This is why at home, if any of you have got more than one computer, you probably only have one actual public IP address, and your cable modem or your router is doing that translation to let you have more than one computer on the network. Do what now? Oh, it wouldn't go through? Yeah, you have to do what's called an address translation. Or based on what type of router you have, some of them have a special port on them now that's called a DMZ. And DMZ stands for demilitarized zone. And what you do, that one port is outside of your firewall. So you plug your gaming device into that one port into the DMZ, and then everything can go through it. The minus to that is security-wise, whatever's in that is open to the internet because it's outside your firewall. Now, being an Xbox, it's probably relatively safe, but that way the ports go through. And then there's another special address called an APIPA address. And APIPA is something that Microsoft kind of came up with, but other companies are using now. Because computers use IP for everything, if you have two computers on an individual network that's not connected to the internet and does not have a DHCP server, they normally wouldn't be able to communicate with each other because they won't get an address. They have no way to talk. Well, a PIPA is a special IP address, and I think we see it in a minute. It's 169 something. I don't remember it off the top of my head, though. Where those two computers, if they don't detect a server, they will pick a random IP address in that 169.254 range, and they'll assign it. They'll first try to ping it with that ping command we saw earlier, and if they don't get a response on it, they'll assign that to themselves. So if two computers are on an isolated network and they didn't find a DHCP server, they're both in that same subnet so they can communicate with each other locally over the network. Another thing you've got to be aware of are the sockets and the ports. And a port simplifies TCP/IP communications. A port ensures that data goes to the service it's intended for. Ports are what allow us to have more than one server on one computer. If it weren't for ports, for example, a mail server could do nothing but be a mail server. It wouldn't be able to be any other server. But because of ports, we're able to have the same things on the same servers. For example, a web server uses port 80 by default. So I can set up a server with port 80 on it, and it can be a web server. You can go to it on the internet. But then I can turn on port 23, and it can be a telnet server. So the same computer can do two services based on whether I connect to port 23 or port 80 will be what I get. And in TCP IPv4, there are 65,535 ports to each IP address. So, I mean, you would never have a server with that many services on it, but you technically could have that many connections on a server. So here they're showing how virtual connection over port 23 for telnet works. You have the request for the connection and then an acknowledgement. Here are the range, 0 to 65,535. There are three sets of these. The well-known ports are 0 to 1023. And those are where services that are set are involved in. Port 80 being a web server, that's in that well-known ports. Port 80 is universally recognized as a web server. 443 is universally recognized as a secure web server. Then 1024 to 49151 are what are called registered ports. They are already assigned to things, but they're not as used as the well-known ports. And then the upper levels, 49152 to 65535, are wide open. Those are for dynamic. Those can be used for just about anything. An example of a registered port, a remote desktop service uses port 3389. That's one of those. There is a list of ports, and here it is. You don't have to know them all, but make sure you're aware of the ones on this table, because you are going to get questions about the known ports on your Network Plus exam. This is one of those areas where I don't know which one you'll get, but you're going to get a question. The question I got on my test gave me a list of ports, and you read the little scenario, and it says you're setting up a mail server, and it's going to have POP3 access, and that's it. It's a mail server needing POP3 access, an incoming email from a server, and they wanted me to know what ports to open. So from that, I had to know that I needed to open 25 and 110. Okay, so we have DNS because people remember names better than they remember words. Who's printing?
I want to print that one page.
All right. So we have the DNS system, which gives us a way to not have to remember numbers. People in general do better with names. Let me give you an example. Imagine if every time you wanted to go to google.com, you had to remember that address earlier, 174 dot whatever it was. I don't even remember it now. People don't do so well with that. So because we can do a DNS system, we have a way to convert names to numbers. DNS is what allows you to put in www.google.com on your web browser, but then that request gets translated into an IP address to go out on the internet before it comes back to you. So in the domain name system, the domain is a group of computers belonging to the same organization that share the common part of an IP address. The domain name identifies it. Here in their example, loc.gov, ours is bipsy.edu. That is the domain for everybody here at Bipsy. The fully qualified host name is the name of the computer and the domain name. So, for example, the fully qualified domain name of the web server for Bipsy is www.bpcc.edu. And you see that written usually in FQDN. Instead of spelled out fully qualified host name, you'll see it as fully qualified domain name in FQDN. So here, another example, and they actually used Google. That's kind of funny. I've forgotten the slide used Google, and I used it earlier. The top level part of the domain, the top TLD is the .com. That's the ending. The top level domains are .com, .edu, .org. There used to just be a few of them, but now there are hundreds of different top level domains. In addition to the big ones, com, org, net, edu, and mil, we've now got countries that have them, like .eu, .uk, all of these countries. And there's money to be made off the internet. Transylvania sold theirs .tv. They got a top-level domain and sold it to a marketing company in California. So now you got a new TV show coming up. You can buy your TV show's name .tv. The third level domain in this is the www, and the second level is the Google. So the dots are, specifying the different levels of the domains. And the group ICANN establishes domain naming conventions. And here in January or February, a lot of this is going to change. The ICANN has now decided that for the first time ever, they're going to allow host names that are not top-level domain oriented. By that, what I mean is like they're going to allow certain companies that have major internet presences to get their name without a dot anything behind it. You will be able, for example, here before too long to go to http://Google with nothing behind it, and that'll come up. Here's a list of some of the common ones. There's so many of them that, I don't think you need to worry about memorizing any of them. Most of you that have played on the internet are going to know some of the real common ones. EDU's a school, ORG's a nonprofit, .com's commercial, Gov is government, mil is military. And some of these you hardly ever see, like Arrow or .coop. Yeah, I've never seen an INT address. Biz is starting to get more popular. What a lot of places have to do now, though, too, because people get confused, if you're a company, you should buy every domain name you can that's around your name. Because they're cheap. Like McDonald's probably, and I don't know this, but I bet they own McDonald's.org, .com, .biz, .us, and probably variations on misspellings on McDonald's. If they're smart, they also own McNuggets.com and, whatever different products they have. Yeah, because they're cheap in the scheme of things, and if people go there, you want them to get to your site, not a redirected. A prime example for a very long time, WhiteHouse.com was a porn site. WhiteHouse.gov is the White House. Somebody bought WhiteHouse.com and made it a porn site. And there was fighting over is that okay or not. And ultimately, it did get taken down when it expired, but the company that owned it was allowed to leave it up for quite a while because they bought it. You used to could do what's called scalping, domain scalping. When a domain name expired at night, at 12 o'clock, it went for sale. So you would look at your competitors and see what's up for sale. And if they didn't remember to renew their domain, you'd sneak in there and buy it at 12:01, and then you owned their domain. So it was possible that you could go to McDonald's.com and get redirected to Burger King because Burger King was smart and got on there and bought it. And now they've decided to extend intellectual property to domain names, which I think is both good and bad. I see the reason behind it. If you want to protect your brand, part of your brand is the internet now, is a web presence. So the way this works is you started out with a host.txt file, and that host.txt associated names with IP addresses. And previous to the DNS system, you had to have a host.txt file on every computer. Now you still use a host file, but the host file points to one of the 13 major DNS servers on the internet. And from there, you're able to get get the names of anything you need. Here's an example of what a host file looks like. And you can use these if you want to redirect DNS to something specific. One of the first network viruses would redirect things in the host file so that when you actually went to Google.com, you were going to their address and you would put in, they had a search page that looked like Google's, but the first things that came up on the search were actually, things they wanted you to look for. They were trying to market to you. So DNS, we talked about earlier. DNS, the way the whole thing works is that you run local servers, and you'll see pictures of these in a minute, that go all the way up to what are called the root servers of the internet. There are 13 root servers to DNS that are the ultimate answer to the way the internet works. If someone were to able to successfully attack those 13 root servers, they could take down the entire internet. And that almost happened once. Only once in the entire history of the internet. And it was a DNS virus, and if I remember correctly, it took down 7 of them. So 7 out of 13, they almost, that's a significant number if you think about it. So the components of DNS are a resolver, which the resolver is any host that needs to look up something. The DNS server is the database of IP addresses to names, and then the namespace is the abstract databases of IP addresses and associated names. So here's an example of how this works. When you need to know an address, first the local DNS server looks for it. And if the local DNS server knows that address, it will reply to it. If it doesn't, it'll send to its ISP to find out from that DNS. If that DNS doesn't know the answer, it'll go to the ISP's DNS. And from there, ultimately, it'll reach one of the main root servers. The root server will send the answer back down, but that answer is cached in all of the servers coming down. So as the answer comes back down, it's stored in those local servers' caches for a certain amount of time. So then when a request goes for that same address again, it doesn't have to go back to the root. An example, Google.com is gone to by somebody here at BIPSI, every hour probably. Our local DNS server is going to know the answer to what IP address Google.com is. But pick something off the wall that no one's gone to, and it may have to go up to our ISP or higher to get an answer. So DNS works by using what are called resource records, and that is one piece of the information. And the type will say what the function is. An A is an address record. A quadruple A is an IP6 address record. A CNAME is the host. MX is a mail record, and the reason we have mail records that are separate, Lots of companies will run their own web server, but they may not run their own email server. So their MX record will point to somebody else. And then a pointer record, which is just a pointer to a name. One that's missing off this list is alias. You can also have an alias that will let you use a different name but be the same thing. For example, if we look up bipsy.edu, well, okay, it's timing out now. Okay, you see there that if we look up bipsy.edu, the actual name for the server that we have here that runs the web server for Bipsy is web.bipsy.edu. But what we go to get to it is www.bipsy.edu. So those are aliases for the same thing. If y'all are to go home today and get on your computer at home and type in http://web.bipsy.edu, you'll get to the web page at Bipsy just like you type www.bipsy.edu. Type web.bipsy.edu. See it here? All right, so if you are a large organization, you're probably going to run two name servers, a primary and a secondary. And that is to ensure your internet connectivity. Here at Bipsy, we run more than two. There are two downstairs, but then almost all of the servers in the different closets for the different buildings have their own DNS server in them as well. So in that earlier picture, you know, where we showed the different ways that things are resolved, here it would be first hit the server in the floor to see if it knows the answer. And if it doesn't, hit the server in the bottom of the building. And if that doesn't know the answer, then go to the main server for the campus, then go to our ISP, then on up and on up and on up until you finally get an answer. So dynamic DNS is something that you can do at home, and it's a way because your IP address changes at home constantly, but if you want to be able to get into your machine, you can assign it a DNS name even though your IP address changes. It is not a DNS replacement. And if you are a large organization, you're not going to use dynamic DNS. You're going to buy statically assigned IP addresses. Bipsy's IP address for www.bipsy.edu doesn't change. That's static. Bipsy pays extra money for it to make sure it stays the same. All right, so application layer protocols are at the very top, and those are what are used to translate requests into readable format. HTTP is one. That is what you use to get on the web. DHCP, that gives you your addresses. Telnet is another one. It's used to remotely log on to clients. It can often connect to dissimilar systems. Telnet is pretty universal, except it's insecure. So the replacement for Telnet is something called SSH, which is encrypted Telnet. The power of Telnet, though, is that you can connect systems that aren't the same type. I can Telnet from this Windows machine into my Linux server back there with no problem. FTP is another one, and it is good to transfer files, but it is also insecure. Secure FTP is the answer to that, and we'll talk more about those later. TFTP is a special one called Trivial File Transport Protocol. And it uses UDP, but it doesn't use any logon. And TFTP is used in a lot of instances to upgrade the firmware on routers and switches. You put your router or your switch in a special mode so that it accepts a TFTP file, and you send it the new operating system with TFTP, and then it reboots and unpackages it and installs it. NTP, network time. This becomes really important in the Windows world because when servers share data, you have to know who's got the newest copy of the data, and that's done usually by the system clock on the computer. So NTP allows you to synchronize the time on all the computers on your network. Ping, which we looked at earlier, ping actually stands for Packet Internet Grouper. But you saw what ping does. Ping tells you if a system's alive. And if you ping 127.0.0.1, you should always get a response. Here's their example showing a ping that worked and didn't work. And that is a quick rundown of the end of this chapter. Do y'all have any questions on chapter 4? All right, in chapter 5, we start talking about topologies. And now we're going to get into more about how networks are laid out. We're going to talk about the advantages of some of the topologies, the disadvantages. I think I've told y'all this before. There's no one answer to most of this. If you take two people who are network engineers that have been doing this a long time and give them a scenario of putting a network in a building, you're probably going to get two very different answers from them. We're going to talk about the backbone structures, the different types of switching, Ethernet networks, and the characteristics. All right, so physical topology refers to how a network is physically laid out. It describes a broad scope, but it doesn't specify connectivity methods or addressing. The fundamental shapes in a physical topology are a bus, a ring, a star, or then a hybrid, which is a combination. Bus is a single cable. All of the computers are connected to that single cable. It uses no connectivity device and one shared communication channel. Usually, physical bus networks use a piece of coax. And the coax would run, if this were a bus network, it would run from every computer to every other computer in the room. It's a passive technology. By that we mean the nodes listen for and accept data, and it uses a broadcast to send. On a bus network, you had to have terminators at the end of the wire. And a terminator was a 50 ohm resistor that you put on the end of the wire. And what that would do is it would end the signal. It would keep it from bouncing back on the cable. And I'll see if I can't find one. I used to have some of these around so I could show y'all. Otherwise, the signal would bounce endlessly on the network. And then one end of the network you would ground to remove static electricity. Here's their example of a bus network. And you see there they're showing what the terminator would look like, and then on one end it's grounded with a terminator. So buses were cheap. Coaxial cable is fairly cheap, but they don't scale very well, and they're difficult to troubleshoot, and they're not very fault tolerant. One cut in that cable anywhere would shut down all the whole network. It would isolate it into two networks. And as far as scaling, imagine if this room were a bus wire and then we wanted to add a computer on the first floor. We'd have to run a cable down to that computer and then back up here, or we'd have to run one down and then terminate it. But then if we wanted to put one on the second floor, we'd have to run it from that first one to the second one and terminate it. So a ring topology connects to the nearest nodes on both sides, and it makes what's called a circular network. And data would flow in one direction around the ring. It is an active topology in that every workstation participates in the data delivery, and the data keeps going around the network until it reaches its destination. Physically, they use twisted pair or fiber. The drawback to a ring is that a malfunctioning workstation can disable the network, and they're not very flexible or scalable. So in a ring, every computer is reading the data of every other computer on the network. This was mainly used in token ring technology. And it's great in a situation like a lab. This would be perfect for ring in here as long as it were just in this room. Because with the computers being connected in a ring, you don't get collisions that you get in bus networks. No computer can send any data till it has what's called the token. So it has to wait its turn so you don't get collisions. In the old days of 10 megabit Ethernet network, this is why Token Ring did have a chance. Token Ring was faster than Ethernet. Token Ring ran at 16 megabits when Ethernet ran at 10. So a star is by far the most common. And stars, every node is connected through some central device, be a router or a switch or a hub. Physically, they use twisted pair or fiber optic, but a single cable connects only two devices. The advantage is they're fault tolerant and flexible. In here, we've got a star network. Every single computer's got a wire that runs into the wall that runs over there to that wiring. So a disadvantage they don't talk about on a star, though, that I'm going to point out, is that there is a single point of failure. There's only one, and luckily that single point is an inexpensive device. But in here, we've got one switch back there. If that switch were to fail, this entire network would go down. But the other good side is if one computer will go down, the whole network would stay up. It's the most popular fundamental layout, and you can have up to 1024 logical network nodes on a single network. So a hybrid is simply a combination of those. And a hybrid is more likely because you seldomly see complete networks that are just one or the other. So some examples of hybrid, you can have a star wired, which has a star physical topology and a ring logical topology, which would give you the fault tolerance of a star, but it's wired like a ring. Here's their example of that, of a star wired. So see, now I've got a switch in the middle, but every computer is connected to that switch with one cable. A star-wired bus is pretty common. This is the basis for Ethernet networks. These computers are physically wired as a star, but logically they act like a bus. Does everybody understand the difference in physical and logical? So that's important to understand, because if we had a hub instead of a switch back there, when one computer talked on the network, all the computers would see it. So in that sense, it's a bus, but they're wired like a star. And here they're showing an example of that. We've got a couple of switches that are hooked together, a couple of computers on one switch, the rest on the other. Logical refers to the way data is transmitted between the nodes. It does not necessarily match the physical. Like we said, the most common is a bus and a ring. And a broadcast domain is all nodes connected to a single repeating device. All right, then we've got our backbone networks. And the backbone is where the routers and the switches are all hooked together. Generally, the backbone has more throughput because it's carrying the data from more than one user. On large organizations, you're going to have a fiber optic backbone. Here on the campus, the backbone between the buildings is fiber optic. Between the floors, you may have Cat5. Like that switch is just hooked with a Cat5 wire to the wiring closet downstairs. Enterprise-wide network backbones are complex because sometimes they cover large distances and a lot of, thousands of users or more. So a lot of planning has to go into them. A serial backbone is the simplest, and in a serial backbone, you have two or more devices. They're just connected together in a daisy chain, which is a length of devices. The benefit is it's easy to grow and it's low cost. Here's an example of a serial backbone. We've got some computers in this room. They're on a switch. We'll run a cable from this switch to another switch with computers on it. Ultimately, that'll run to a router. Serial backbones have a limited distance between each network, though. So that's why there's only a certain number of repeating devices. And they say that a serial backbone is not used in a modern network. I'm going to argue that a little bit later. And the reason is, much like you saw earlier, we talk about hybrids. Most backbone networks are hybrids now too. You're not going to find any one fit. Part of our network here is a serial backbone because of the way this room is wired. That switch goes to the switch in the wiring closet for this floor. But then we go downstairs and we get on the backbone and we're a ring because we got a fiber ring running between the buildings. So again, there's not one answer. A distributed backbone uses connectivity devices that are connected to some central device. The benefit is simple expansion and limited capital outlay. They can connect multiple LANs. Distributed backbones give you the advantage of work group segregation, and they may include daisy chain linked and repeated devices. But again, we got to consider the length. The drawback is the potential for single point failures with all the switches. Here is a distributed backbone. And you see we've got one router, we've got switches in different places run into that router, and in some places switches are run from those other switches. Here is another distributed backbone with multiple LANs and routers. A collapsed backbone uses a central connection point for multiple networks. At the highest layer, you have a single router or switch with multiprocessors. There is risk of that central failure, but it also gives central management. And this is an example. This is something kind of like what we have here at BIPSI. We have one router downstairs that you'll hear people call a core router. And it's a very large router, and it handles all the traffic for the entire campus. But all of the traffic from the other campus comes in from different switches or routers that are part of our network, and then it reaches our core, and the core is what actually connects us out to the internet. So your core device there is usually an expensive device, but it does more than just routing. You see there they've got those blades. Those are called blades in it. And like, I'm not sure about the one here, but like the one for LSUS, our core router was also our firewall. It was our content management. It was all the different things we had on the campus. And they were each separate little blades that went in this one server. And that one server had two power supplies in it that were run off two different UPSs. So even though it was one device as a central point of failure, it had redundancy built into the device. A parallel backbone is the most robust. It uses more than one central router. It gives redundant links, increased performance, and fault tolerance, but it's, of course, more expensive. Here they're showing an example of a parallel backbone, and you'll notice two wires are run to every place. Redundancy is always best, but it's always going to come at a cost. And you just, as a network admin, you've got to figure out what kind of money is available to spend on your network and how important it is. A redundant, parallel to this room would be nice, but if we have a failure, okay, so we're down for a day. It's an acceptable problem versus what we would spend to have two of everything in this room. To be fully redundant, we'd even need to put two network cards in all the computers in here and run two sets of wires to two switches that would then run to two other switches that would run two wires down to the server room. It would cost twice as much, exactly. So for some things, that's worth it. Some things you need that much. Our internet connection over at LSUS, we had two internet connections because keeping our web server up so that students knew what was going on in the event of, something happening on the campus was important. But we didn't make redundancy for all the computers on the campus because that would have been an expense we didn't really need. You just pick the things that you need to be redundant. So switching is a logical network topology component. And switching creates connections between nodes. And there are three methods of switching: circuit, packet, and multi-protocol label. In circuit switching, the connection is established between two nodes before data is sent. That means it's dedicated bandwidth. You use this for live audio and video conferencing, and a traditional telephone call is a circuit switch network. In the old days on the phone, when you picked up the phone, there was actually a connection going between two wires from you to two wires from whoever you were trying to talk to. Packet switching is more popular though, and it breaks the data into packets before it's sent out. That way they can travel any network, they can find the fastest packet. They don't actually have to follow each other, and they're reassembled at the destination. It requires speedy connections, however, for audio and video. MPLS is another one, and this is a multi-protocol label switching. And this enables layer 3 to travel over different layer 2 networks. And commonly this is used in layer 2 WAN protocols. It offers potentially faster transmission than packet or circuit switch networks. Here they're showing an MPLS, and the reason is because it has better quality of service. So Ethernet is by far the most popular technology. Ethernet's flexible, it can run on lots of different media, and it's pretty reasonable cost. They share a common access method, and this is an acronym you're going to need to know. CSMA-CD, and the other one is CSMA-CA. And what that stands for is Carrier Sense Multiple Access Collision Detection. And here we're going to explain it. What Carrier Sense Multiple Access Collision Detection is, that means that a computer tries to, before it talks on a network, it listens and it tries to see if anybody else is talking. And if it doesn't hear anything, then it assumes the line is clear and you can talk on it. You can kind of think about this, I think I used this example with y'all before, like a party line. Are any of y'all old enough to even remember party lines? You know, an old party line, you had to pick it up, and if your neighbors were on it, you'd hang it up quietly until they got off. Well, that's kind of what this is. The Carrier Sense, you'd pick it up. But if they had made a call and you didn't know they'd made it, and you pick it up and start dialing, then you're going to get a collision, and that's exactly what happens if two computers on a network talk at the same time. So here a collision, two transmit simultaneously. So when a collision detection happens, you've got to have some sort of routine to figure out what to do with it. And the way that happens, jamming, it's a 32-bit sequence the network card does, and it indicates that the previous message was faulty. So on networks that had hubs that were large and had a lot of traffic, collisions were common. So as your segment grows, the performance would suffer because you'd reach a point where data had to be retransmitted so much that more network time was spent retransmitting data than actually able to send things on it. So collisions corrupt data and truncate data frames. Here they're just showing how the process works. A station listens for activity. If it hears something, it waits. If it hears nothing, it would transmit. If once it transmits, it detects a collision, then it'll stop and a random number will go off between the two computers. One of them will get to transmit and the other one will have to wait. So a collision domain is the portion of the network where collisions occur. Repeaters repeat collisions, but switches and routers separate collision domains. That is why we don't use hubs anymore, we use switches. Remember I told y'all a hub just sends out whatever it hears, but a switch actually listens and only sends data to the port that it wants. So what happens is with a hub, you've got, say 3 computers, and over here I'll do a switch, and I'll put 3 computers. In a hub, this is all one collision domain. In a switch, every single port is a separate collision domain. So the chances of a collision are much, much less on a switch than on a hub. Because the switch will take, when you send data from this computer to this computer doesn't even see it, just these two, because that's where it's destined for. But over here with a hub, it transmits everything it sees. So this computer may send data to computer 2, but all the computers are going to see it. So are y'all understand the difference in a switch and a hub? In the old days, you used hubs because they were cheaper. But nowadays, switches are just as cheap as hubs used to be. So basically, the rule should be use a switch if you're building a network. Don't mess with a hub for any reason. And if you're trying to improve the performance of a network and it's got a hub in it, pull that hub out and put a switch in it. You'll dramatically increase your network. Here's their graphic showing what I just showed y'all. A hub does not break up a collision domain, but a switch does. Now, broadcast domains are only broken by routers. So you notice even though that switch creates different collision domains, they're the same broadcast domain. Make sure y'all know the difference in those, how to know what a collision domain and a broadcast domain is. You might get a question on the test where they give you a diagram, something like this, and ask you how many different collision domains there are, how many different broadcast domains there are. And the way you know the difference is that a router breaks up broadcast domains and a switch breaks up collision domains. And a hub doesn't do anything but repeat data. All right, so CSMA-CD again. Ethernet cabling is affected by collision domains. There is a propagation delay, which is the time it actually takes the data to travel out on the cable. With 100 or with 1,000 megabit networks, 3 segment maximum connected with 2 repeating devices. With 10 meg buses, 5 maximum connected with 4 repeating devices. Now remember, switches reset all of this. We're talking hubs here. There are different standards for the wire as well, and those are all set with the IEEE, and based on the encoding will determine the throughput, the segment length, or the wiring requirements. 10 base T, the 10 represents the throughput, 10 megabit. Base is baseband, the T stands for twisted pair. And they say follow the 5-4-3 rule. 5 network segments, 4 repeating devices, and 3 populated segments maximum. But also remember that that doesn't apply if you're using switches. This is back to hubs. A switch resets everything because it regenerates the signal. A hub doesn't regenerate anything. It sends the data out as is. So here they're giving an example. Notice those are all hubs. 100 base T, that's fast Ethernet. Similar to T, it's a baseband star RJ45 connections. Supports 3 maximum networks. 100 meters is the key number there. You might get a question that says something about what the maximum length on a Cat5 cable is. It's going to be 100 meters. 100 base TX is full duplex over twisted pair. Here again, they're showing the same one. 1000 base T, that's your gigabit network. You use all 4 of the wires, 4 pairs of wires in a Cat5 cable. The data in scheme is different from 100 base T. Maximum length again, 100 meters and 1 repeater. 10G base T, just faster. This is 10 gigabit. This is pushing the limits of twisted pair cable. 10 gigabit over copper is getting to just about the end of what we're going to be able to see. 100 meters again, very fast data transmission and cheaper than fiber optic. Then we get into our fiber. 100 base FX is 100 megabit baseband fiber. 1000 base LX is gigabit Ethernet over multimode. 100 base SX is short wavelength over multimode. 1000 base SX again, this is just all the different standards. I'm going to kind of skip through some of these. You're not going to need to know the absolute details for these on the test. But if we skip up here to slide 58, this is something I would take a little bit of time to learn. The difference is in the standards, just the main thing you need to know. Be able to recognize the speed and the length from these. You see, if we use some of this big one, 10G base ER and EW, we can get 40,000 meters out of it. That's some of the really long distance stuff. Here they're showing too that you can use multiple types of Ethernet on a wide area network. Because you can use switches to change things in media converters, your network doesn't have to be wired the same way. You can have part of your network that's 10 megabit, part of it that's 100, and part of it that's gigabit, with different switches and routers in different places to convert the speeds. All right, so Ethernet frames. Frames are how you put the data actually out on the network. And there are 4 types, a .2, a .3, Ethernet 2, and SNAP. They're slightly different in the way that they're coded, but they don't have anything to do with the cabling or the topology. 802.2 is one of the older ones. .3 was Novell. You used to have networks that run 2. Ethernet 2 is an older one, and then SNAP. And even though Ethernet 2 is a little older than VIX, it's what's kind of commonly used today. You define that with your network card. And in the old days, you had little dip switches on those network cards you would switch. But nowadays, it's auto detect. And this almost really doesn't matter anymore because it's all going to be automatically done for you based off what type of switches and hubs and things you have. So your frame field is what tells the network that a frame is coming. It has 7 bytes in the front, then 1 byte to start the frame, then 14 bytes as a header, and then the actual data. The larger you can make your frames, the faster the output's going to be. Here's what Ethernet 2 actually looks like. It was developed by DEC, Intel, and Xerox. That's where DIX come from. It contains a 2-byte field, and it's most commonly used on Ethernet networks. So the last thing in this chapter, which is why I know I'm going a few minutes over, but so we can get on through it, power over Ethernet, the 802.3 AF standard. That is something that's been around a while, but it's really catching on now. And what it does is it allows you to put an access point or other device on your network that needs power without you having to run a power brick to it. The reason this is so popular is for like wireless networks where you're trying to do networks now. You may put the network up in the building, but you don't know where you may not have power where you want to put it. So you run that and it actually runs power to the device over the same cable. Lots of voice over IP phones use power over Ethernet. So you don't have to run power to the phone. It's still going to get it off the line. And it's low voltage power, but it's enough to run some of these low devices. It's not a lot more power than actually what USB has. Here they're showing a PoE switch, and that PoE switch is going to put power in it automatically. If you don't have one of those, but you need power for one device, what you do is those devices on the side are called injectors. And you run your cable into it, and it puts power over Ethernet into the cable for your cable run. So that is a quick rundown on Chapter 5. Y'all? Oh, go ahead. Do y'all have any questions?
One thing I learned recently is on the NIC where it has an orange and a green. If that thing has a red light on it, don't plug into it unless it's designed for PoE, because that means it's hot. If it's got a red light on it, that means it's got power.
It's got power.
Mm-hmm.
Most of the newer power over Ethernet switches have what they call a negotiation on them. And what that negotiation does is it allows you to plug in a device, and it will determine if it needs the power or not. And the reason for that is because, let's say you got 6 devices, but you bought an 8-port power Ethernet switch because 2 of them needed it. You don't want to have a second switch for those other devices. So those ports will turn themselves on, and they'll first see if they get data back without power. And if they don't detect anything, then they'll send a little power to try to power up the device. So they're getting smarter and smarter with this stuff, which is good because a lot of the problems that we talk about in here for y'all to realize, they're old problems that don't exist anymore. Like where we're talking about hubs and collision domains and how that used to be a problem. You don't see hubs anymore. Unless you're going into a very, very old network, it's not going to have hubs. It's going to have switches. and that takes care of collisions. But Ethernet still has all that collision detection because it's still standard all the way back. You can take that 1000 speed hub up there, switch rather, and plug in a 10 megabit Ethernet card, and it'll work. It'll drop the whole network to 10 megabits, but it'll let you connect it. So any other questions on 5? All right, well, we will do 6 on Monday. We'll see if we get into 7, and then from that I'll determine what I need to pre-record for y'all for the next couple of days. I will go ahead and work on the rest of the chapter quizzes. 1 through 5 are up, so take them whenever y'all are ready. Remember, don't open it till you're ready. And all of the videos, if y'all, I know some of these have been a while now. I've got all the videos online, so if you want to go back and watch any of the class videos before you take the test, feel free to do so. I'll see you guys on Monday.